So, in these areas where, again, the soil is characterized by relevant permeability, groundwater is an interesting option. Groundwater is also an interesting option because it's more protected with respect to pollution. With respect to river flow, of course, groundwater is less exposed. It's less exposed to several potential contaminant sources, including natural ones. And also, groundwater usually reaches the final water body where it resides through typically filtration, through infiltration and then filtration operated by the porous media which hosts the groundwater body itself. So for these several reasons, groundwater is an interesting option, and in fact that we know, starting from the antiquity, several human settlements had the idea of excavating wells for getting water from the underground. As I said, groundwater typically covers an important portion of water uses, both civil and agricultural, and also industrial water uses. In some regions, like the Emilia-Romagna region, it covers a dominant part of the water uses. It has many advantages that I already mentioned to you. First of all, besides these advantages, which I already mentioned, which are easy availability and usually high quality, besides these advantages, groundwater has other advantages and disadvantages. Another relevant advantage is that groundwater has turnaround time, replenishment and depletion time that is longer with respect to surface water, which means that groundwater usually is sped up by rainfall in a longer time, and also when the aquifer is sufficiently extended, for the presence of relevant volumes, has a depletion time and exhaustion time that is longer. The overall cycle has a different timing with respect to the cycle of surface water. So the overall cycle of replenishment plus use, depletion, has a different timing. It's longer, but in any case what's relevant is that it's different. The result is that groundwater is typically available also in the dry season, which explains why it's widely used. Surface water in the dry season becomes less and less available. Groundwater remains typically available also in the dry season because, as I said, the cycle, replenishment, use, depletion has a different timing. So typically, in several regions, we use surface water for feeding water resource systems. In spring, fall, in our climate, when surface water is typically available. In the dry season, summer, we tend to use groundwater. We use groundwater because it's more easily, more readily available in the dry season. There are disadvantages. One practical disadvantage is that typically groundwater needs to be pumped. Not always. I already mentioned to you that there are groundwater bodies called artesian bodies, which are confined, meaning that the groundwater is in between two impermeable layers. I think I have a slide somewhere. And therefore, being confined, if we excavate a well and through the upper confining layer, groundwater comes to the surface without pumping because it's compressed between the two confining layers. So if we excavate through the upper layer, groundwater comes to the surface spontaneously. I'm looking for a slide, provided I can find it. Let me see. Here it is. Here it is. You see, this is a confined aquifer, meaning that there are two confining impermeable layers, the upper one and the lower one. If we dig a well through the upper confining layer, the water is under pressure here. It's under pressure because it comes to the confined aquifer from the mountains, so there is gravity from the upper sources that is pressing water, is putting water under pressure. If we dig the well through this confining layer, we obtain what's called an artesian well that gives opportunity to get water to the surface without pumping, because it is brought to the surface by the energy of the pressure. The unconfined aquifer, conversely, which is also called phreatic aquifer, it's not confined, of course, as the term suggests, and therefore, if you dig a well into the aquifer, you need to pump water. This is typically what happens. Confined aquifers are less frequent. The most frequent case is the case of phreatic aquifers, unconfined, which means that we need energy to pump water to the surface, and this is a first practical disadvantage. It is a relevant disadvantage because energy has a cost, and this is the reason why farmers typically they prefer to use water from rivers, which comes by gravity to the field directly, with respect to using groundwater, which they need to pump. This is a first disadvantage. The second disadvantage is that groundwater is less observable with respect to surface water, and this is a problem. It's a problem because in principle we don't know before digging a well whether there is water enough in the aquifer. So typically, in the past, we used the trial and error procedure, which means that people tried to dig a well, and then they started using the water. And by using the water, they made practical pumping experiment, which confirmed how much water is available and when it's available. So they realized, for instance, that some wells during the summer went dry. And therefore, they tried other options, like digging another well, or putting the well more in depth. Because, of course, if you go more in depth into the soil, you find other aquifers, which may be confined, and therefore, if you are lucky, if they were lucky, they could find artesian aquifers that allow them to get water to the surface without pumping. Or, in any case, they found other aquifers where more water was available. It was a trial and error procedure because, of course, you can't see what's in the underground. Today, we have some monitoring techniques that allow us to get a deeper knowledge, but still, this is not an easy problem. And typically, people, when they dig wells, they go by experience. They know, because they did many others, they did many other wells, they know that in a certain location they find a first aquifer at a given depth, and then they know that if you go more deep, they find another aquifer at another depth. And also by experience, they know what is the pressure of these aquifers. They know how much they have to pump in order to get water to the surface. This is typically how it goes today. So we know, for instance, that in the Emilia-Romagna region we dig a lot of wells, so we know what is the depth, what are the aquifers, what is the depth of each of them. And this is the way we follow. It's based on our expert knowledge, which is in turn based on several trial and error procedures that humans made in their history. we also have some means today of making tests, more advanced tests, like instead of digging a big well, we dig a small one, a very small one, which allows us to inspect with more detail and less costs what's in the underground. But still, estimating what's the water availability, so estimating what is the limiting flow that we shouldn't exceed while pumping, still remains a challenge, because the only way is to try. And sometimes we don't know what is the extension, the lateral extension of an aquifer. We find an aquifer at a given depth, and then we start pumping and try to see how it goes. Another limitation is that we don't know the recharge time of the aquifer. So we may find a lot of water, we start pumping and we see that indeed there is a lot of water, but who knows, maybe that after 10 years of intensive water use, water is depleted and we don't know what is the recharge time. Because for some aquifers, the recharge time may be 1,000 years. It's a very slow process, which at the end of the story brings water that is generally high quality, but so what are the disadvantages? Basically energy and limited knowledge of water resources availability. And how to resolve the problem of limited knowledge? By trial and error, and you may find an analogy with the river flows, where you make observations and estimate a flow duration curve. With groundwater, you basically do the same. You make observations. Of course, it's more complicated because you don't see it. So you need to dig holes, large holes, wells, very small holes, piezometers. You need to make experiments. And if you have limited observation, like for river flows, an option is modeling. So we try to model the dynamics of the aquifer. Keep in mind that aquifer means groundwater body. So aquifer is made by a porous media, because without pores you don't have any possibility to store water. A porous media with water in it. Therefore you understand already now that porosity is of the media. The porous media is an essential behavior. Porosity is given by the volume of voids in the porous media divided by the total volume. So porosity E is given by the volume of void divided by the total volume. So you have a porous media and you have a total volume, so WT, and the volume of voids. And this volume of voids is given by V subscript V. And if you divide the volume of voids by the total volume, you obtain porosity. Of course, you understand that porosity may vary between 0 and 1. And also you understand that porosity, volume of voids, depend also on the size of the grains that compose the porous media. So if you have a coarser size of the grains, so if the grains are bigger and they are not well mixed in terms of diameter, you obtain more voids. If the grains are very, very small, very tiny, and or they are well mixed in terms of diameter, you have a more compact medium, and therefore the volume of voids decreases. Porosity is an essential property. Another essential property is a measure of the connection between the voids, which allows water to flow through the porous media. And this is called permeability, which is measured through a kinetic property which is called hydraulic conductivity. We will define it later. So again, connectivity between the pores, which defines permeability. Permeability is a physical property. The measure of permeability is hydraulic conductivity. Keep in mind that not necessarily high porosity means high permeability. Usually yes, because if you have bigger pores, of course it's easier that they are connected. But it happens in some cases that you have large pores that are not connected, and therefore they may contain water, but this water is isolated. There is no connection. We are interested in media that are characterized by relevant porosity, because this means relevant potential storage, but also relevant hydraulic conductivity, because it means that there is a water flow in it, a potential water flow at least. We are interested in the water flow because when we get water from an aquifer, basically we withdraw water. So there were voids that were occupied by water that after our taking, now they are empty. And we are interested in getting them replenished, getting new water into them, because otherwise, of course, we take the water, and then if there is no water flow to fill the pores that we have emptied, we don't have any opportunity to withdraw more water. So we are interested in the permeability because our withdrawal triggers, gives rise, originates water flow into the aquifer. We are interested in the fact that this water flow can happen. And therefore, again, we are interested in porosity, but also hydraulic conductivity. Okay, let's go back to the models, the groundwater models. Why we are interested in applying a model? Because we are interested in trying to understand how the aquifer works, how water moves into the aquifer. This is our interest. To understand how water moves into the aquifer, how the aquifer is recharged through water flow. We are interested in knowing how long it takes to recharge the aquifer. We are interested in knowing, at the end of the story, the amount of water that we can withdraw from the aquifer in a sustainable way. Sustainable in this case means that the withdrawal is compensated by recharge. As long as our withdrawal is compensated by recharge, we are fine. Compensation may take place in the long term. It's not necessary that it takes place in a short term. Like if I get water today and the aquifer gets replenished in 6 months from now, it's not a big problem. The only thing is that in a, let's say, in a seasonal cycle, we are interested that in a seasonal cycle there is compensation. If it happens that after the closure of a seasonal cycle there is a decrease of groundwater availability, we are concerned because this decrease may repeat itself for the subsequent year and so forth until to the time where there is no more water in the aquifer. So the idea is, let's try to apply a model. And basically, the structure of these models is very similar to the structure of river flow models, because we are talking once again about water flow. So, offshore, of course, the physical bases are identical. Physical bases of the water flow are identical, and it's understandable that also the equations are the same, the equations governing the process. If the physical bases are identical, the equations must be the same, and the model structure, as a consequence, is the same. What's very different is the geometry of the control volume. Remember, the control volume is the portion of space where we study the movement of water, and as a result, it's the portion of space where we apply our equations. And I said that for the river, usually the control volume is a piece of river. It's a reach of the river between two given cross sections. In this case, the control of volume, the control volume is, in our case of groundwater, is the aquifer itself, or a portion of it. And therefore, you understand that describing the geometry of an aquifer is much more complicated than describing the geometry of a river. It's not easy also to describe the geometry of a river. We need to call into play a surveyor and ask him to make a survey of river cross sections. In the case of the aquifer, the problem is even more complicated because we don't know what are the limits of the aquifer. We have to inspect them. And what's perhaps even more important, we don't know the geometry of any single pore. We cannot describe it. In order to describe water flow in detail, we need to describe the geometry of the contours of the water flow. And in this case, the contours are the contours of pores. There are millions, billions of pores that, if we want to describe the flow in detail, the groundwater flow in detail, we should consequently describe these billions of pores, which is impossible, as you can understand. And therefore, we need to make assumptions. And it's clear that we cannot describe the river flow in detail, at the detail of any single pore. It would be sufficient if we could describe the river flow on average. What do I mean by average? Think about a well. We have a well. The well, water coming into the well, is the result of water flowing through millions of pores. I don't need to know how much water comes from each pore. It's enough for me to know how much water can be delivered by the well, which is an average at the end of the story. The well is the resulting from averaging millions of pores. But if we could describe then water flow, groundwater flow on average, we would be happy. It wouldn't be a problem. Okay. So let's go into the detail of groundwater models. And there is an equation which is called the groundwater flow equation, which is also described on Wikipedia, that we need to derive. It's an interesting story to derive this equation. Basically, we need to apply again mass balance and energy momentum balance equations, because as I said, the equations are the same. we need to make some assumptions, and it's an interesting story to combine these two equations with reference to a groundwater body in order to get the groundwater flow equation. We will not go into the same detail as for surface water, meaning that I will set the basis, I will derive with you the groundwater flow equation. We will not move into application, and we will not make practical examples. The reason is that applying a river flow model is easier. Let's say that it's easier to make a simple application of them, like the linear reservoir. If you think at it, it suffices that I give you a time series of precipitation and then a time series of observed river flow, and you can make a simulation quite easily. For groundwater, it's more complicated, and the only way to make simple computation is to introduce empirical relationship, like Darcy law, which we will discuss, and you probably heard already the Darcy's law. And but reviewing and applying empirical equations, I think, doesn't add too much to our knowledge. So this is the reason why I prefer not to go into the details for groundwater flow. There is another reason, which is the fact that it's less frequent to apply groundwater models with respect to river flow, rainfall runoff models. But one thing that I would like to tell you, there are public domain softwares available to apply groundwater models, and if you are interested, this is something that can certainly be inspected with more details, but this is something that I leave to you. It may be interesting because it's an expertise that is less frequently available from professionals, and also it's an active research field, but as I said, we don't have enough time to go into the details of this. And in fact, we have courses, and probably you have them already available on groundwater modeling, so I'm not going into the details. Okay, so let's take a control volume. Let's take a control volume and whatever shape. Let's take a cube, and basically this control volume may be the region of space that is occupied by an aquifer. So let's assume that this control volume is completely occupied by an aquifer, and let's take this control volume with infinitesimal size. So this is a cube, as I said, and let's indicate with the x, the y, and the z its dimensions, its sides. And let's assume that we have a flow of water entering and therefore exiting from the three directions of the space which make the sides of this control volume. So let's suppose that we have a Qx, which is a flow per unit area, specific flow. This Qx is a flow per unit area, and therefore it may be expressed as a length divided by time, like meter per second. It's a velocity, basically. Flow per unit area is a velocity. Let's suppose that we have a flow along the direction x, entering from here, which implies that we potentially have a flow exiting from the opposite face located on the same x direction, potentially, maybe zero. I mean, the flow may enter from x and go out from z, but potentially, let's suppose that all of these faces are permeable and therefore potentially hosting flow. And then we have an analogous flow Qz along z and an analogous flow Qy along y. Okay, it's clear that we have the need of admitting these flows because we want water flowing through this volume. And it's clear that if we have flow, we can apply a mass balance equation in it, which is very simple. and let me introduce it. Oh, let me make some assumptions first. Sorry, I forgot them. This is a mass balance, but let's make some assumptions. Let's assume that the flow is incompressible. And let's exclude source term inside the control volume. You understand why I make these assumptions, because these allow me to apply the mass balance equation in an easier way. If the fluid was compressible, applying the mass balance equation would need to take into account compressibility. So the fact that mass can be compressed into the corresponding volume. If I exclude this possibility by assuming that the fluid is incompressible, I imply that the mass density of fluid doesn't change. The second assumption, no sources, excludes that you may have fluid sourcing from the volume, inside the volume, and therefore it means that the only sources of fluid into the control volume may occur through the phases. You don't have any source of fluid internally. And then you can easily write the mass balance equation, which is the same mass balance equation that we applied for the linear reservoir. The change in time of the volume of water inside the control volume is given by the total amount of inflow, you see the capital Q here, minus the total amount of outflow. You see here dependence on 4 coordinates, and this is why the location of the control volume, which has, as I said, an infinitesimal volume, the location is varying in space. The location can be any in the 3-dimensional space covered by the aquifer, and therefore the volume stored in this infinitesimal, the volume of water stored in this infinitesimal control volume is depending on space, on the 3 spatial coordinates, and also changes in time, because this is a dynamic process. Of course, it may happen that some variability can be neglected. But now, these are variables depending on 4 independent variables: x, y, z, and t. I am interested here in expressing the change in time, so this is why I studied the variability in time. And then by exploring other regions of the control volume, I can explore variability in space, but now I'm interested in variability in time, which is given by changes in inflow and outflow. And again, I draw your attention on the capital Q, which means overall inflow through the 3 phases, through the 3 directions, and overall outflow through, again, the 3 direction, x, y, and z. This is quite simple. Okay, but here we have several unknowns. Let's see how we can move forward. Don't be concerned by this slide, because it's very simple. Now we have to move forward by basically writing the inflow as the sum of the inflow through the 3 phases. So basically what we have to do is, in the previous slide, I go back because the previous slide is less concerning, there is only one equation. So now the next slide, the purpose of the next one is to write Q in and Q out as the sum of the corresponding flows through the 3 phases. I go back once more. You see here, Qx Qy, their sum gives capital Q in In. And then we have an outflow, which may occur in the opposite phases. Again, it's the sum of the outflow along x, y, and z. Again, we don't necessarily have all of these components. Some of them may be zero. So the flow along z may be zero. Or the outflow along z may be zero. In the general treatment, this is a three-dimensional problem, depending also on time. So, from this equation, we have to find a way to write Q in and Q out as the sum of three components. Okay, perfect. Now let's go here and let's look at only the last one. Okay, because, or let me see, let's look at this equation here. Let's forget about what's written above because I already said that. So, Q in is given by Qx, the sum of the three components along the three directions, so Qx, but Qx is flow per unit area, as I told you before. Lowercase q is flow per unit area. And therefore, I have, in order to get the total flow entering through x, I have to multiply the flow per unit area times the area of the x phase, which is given by the y to z. So you see, it's very simple. Plus the flow through y times the x, the z, plus the flow through z. It's very simple. This is what's the purpose of this slide. So there is not much to learn. And let's look at Q out now. Q out is a bit more